Welcome to your deep dive into a brief history of time. You wanted to explore the universe, so we're taking you on a journey guided by Stephen Hawking himself, or at least his brilliant book.
Yeah, this book is a classic, because it tackles huge questions like how did the universe begin? What are black holes really like? And is time travel even possible?
Exactly. It's amazing how Hawking takes complex physics and makes it understandable, even throwing in some mind-blowing possibilities along the way.
Right. What we're going to do is trace the evolution of our understanding of the universe from the ancient Greeks all the way to the latest theories about black holes, the Big Bang, and even time travel.
Okay, let's unpack this. The book starts by taking us way back in time to see how our picture of the universe has changed over the centuries. It begins with the ancient Greeks, like Aristotle, around 340 BC. What's fascinating is that he figured out the Earth was round without any fancy telescopes or satellites.
He was a keen observer. You know, he noticed things like the Earth's shadow during a lunar eclipse is always round. And travelers coming back from the south said the North Star appeared lower in the sky compared to when they were further north. Plus, there's that classic image of ships disappearing hull first over the horizon. All those clues pointed to a round Earth.
Pretty smart for someone living over 2,000 years ago.
Yeah.
But then we get to the Ptolemaic model, which put the Earth at the center of the universe. It kind of worked for a while, but it had some serious flaws, right?
The Ptolemaic model was pretty clever for its time. It tried to explain how planets and stars moved, but to make their calculations work, they had to come up with some strange explanations, like the idea that the moon's orbit sometimes brings it twice as close to the Earth.
Which, if it were true, would make the moon look twice as big in the sky sometimes. But we know that doesn't happen.
Exactly. That was a major problem with the model. Then along comes Copernicus in the 16th century, who says, hold on a second. What if the sun is actually at the center? His heliocentric model was revolutionary, not just scientifically, but also because it challenged the church's view that Earth was the center of creation.
Copernicus's idea really shook things up. Imagine living in a world where everyone believes the Earth is the center of everything, and then suddenly you're told that's not true. It was a huge shift in perspective. And then Galileo comes along and supports Copernicus's theory with his own observations using a telescope.
Yeah, Galileo saw things like the phases of Venus and moons orbiting Jupiter, which couldn't be explained by the Earth-centered model. He got in big trouble with the church for supporting the heliocentric view. It really highlights how new scientific discoveries can challenge deeply held beliefs.
It's fascinating how scientific progress often means going against the grain. But let's not forget another giant in this story, Isaac Newton. He literally wrote the book on gravity, and his law of gravity explained why planets move the way they do. His ideas were so powerful they were accepted for centuries.
What's interesting about Newton is that while his law of gravity was groundbreaking, he still thought of space and time as absolute and unchanging. Little did he know that another revolutionary thinker would come along and completely change our understanding of those very concepts.
Hmm.
I'm talking, of course, about Albert Einstein.
Einstein is where things get really interesting. He basically turned the world of physics upside down with his theories of relativity.
Yeah.
We're not talking about just one, but two theories, special relativity and general relativity. It can get confusing, so what's the difference between them?
Well, special relativity deals with objects moving at constant speeds, like a spaceship cruising through space. Einstein had this radical idea the speed of light is always the same no matter how fast you're moving. Think about it. If you're driving at 60 miles per hour and throw a ball forward at 20 miles per hour, someone standing still would see the ball moving at 80 miles per hour, right? But with light, it's different. Whether you're standing still or zooming through space, you will always measure the speed of light as the same constant.
That's so counterintuitive. It seems like the speed of light should change depending on how fast you're moving, just like the ball in your example.
Exactly. And that's what's so mind-blowing about special relativity. It turns out that to keep the speed of light constant, our measurements of space and time have to change. They become relative, not absolute.
Okay.
There's a famous experiment, the Michelson-Morley experiment, where they tried to measure the speed of light in different directions as the Earth moved around the sun. They expected to see differences, but they found none. The speed of light was always the same.
So this idea that the speed of light is constant led to the concept of space-time, right?
Right. Space and time are intertwined, forming this unified fabric called space-time. And special relativity even gave us the famous equation EMC20-OR, which shows that energy and mass are fundamentally connected. Matter can be converted into energy, and energy into matter.
Wow.
It's a pretty big deal. And it's what powers things like nuclear weapons and the sun.
Okay, so special relativity already blows my mind, but then Einstein takes it up another notch with General relativity, what's that all about?
Well, general relativity expands special relativity by including gravity. Einstein's big insight was that gravity is not a force acting at a distance like Newton thought. Instead, it's a consequence of the curvature of space-time.
So you're saying massive objects like planets and stars actually warp the fabric of space-time around them?
That's exactly it. Imagine a bowling ball on a trampoline. It creates a dip in the fabric, right?
Yeah.
Well, massive objects do the same thing to space-time. They warp it, and that warping is what we experience as gravity.
That's a really helpful way to picture it. So when we see an apple fall from a tree, it's not that the Earth is pulling on the apple. It's that the Earth has warped space-time around it, and the apple is just following the curvature.
Precisely. And we've actually seen evidence of this warping.
Huh.
During a solar eclipse, the light from distant stars bends as it passes by the sun. This happens because the sun's mass warps space-time, causing the light to follow a curved path. It's a pretty amazing confirmation of Einstein's theory.
Okay, so gravity is not a force, but a warp in space-time. That's going to take some time to wrap my head around. But speaking of warp space-time, this brings us to black holes, one of the most mysterious objects in the universe. What are they exactly?
Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives. You see, stars are constantly fighting against their own gravity. The energy produced in their core pushes outward while gravity pulls inward. But when a star runs out of fuel, gravity wins and the star collapses. If the star is massive enough, this collapse continues until its density becomes infinite, creating a singularity.
So a black hole is essentially a bottomless pit in space-time. Once you cross the event horizon, there's no coming back.
That's right. The event horizon is the point of no return. Once you cross it, you're inevitably drawn towards the singularity at the center of the black hole. And here's where Stephen Hawking made his groundbreaking contribution. He showed that black holes aren't completely black. They actually emit a faint radiation due to quantum effects. It's called Hawking radiation, and it means that black holes slowly evaporate over time.
Wow, so even black holes eventually fade away. That's incredible. Hawking's book doesn't just focus on black holes, though. It also dives into the origins of the universe and the Big Bang Theory, which brings us to another mind-bending concept, the expanding universe.
Right. We know that the universe is expanding because we see distant galaxies moving away from us, and the farther away a galaxy is, the faster it's moving. This discovery made by Edwin Hubble in the early 20th century changed our entire understanding of the cosmos. It means the universe is not static and unchanging, but it's constantly growing.
It's like a giant cosmic balloon that's being inflated. So how does this connect to the Big Bang?
If we rewind this expansion, it suggests that everything in the universe was once incredibly close together, packed into a tiny, hot, and dense point. Then about 13.8 billion years ago, this point began to expand rapidly in what we call the Big Bang. This expansion continues to this day.
So the Big Bang is not an explosion in space, but rather the expansion of space itself, right? It's not like something exploded into something else.
Got it. And there's actual evidence for the Big Bang. In the 1960s, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates the entire universe. It's like the faint echo of that initial expansion, and it provides strong evidence for the Big Bang theory.
That's amazing. We can actually detect the remnants of the Big Bang, but this raises a big question. What came before the Big Bang?
That's a question that has puzzled scientists for decades, and it's one that Stephen Hawking explored in depth. He proposed a concept called the no-boundary proposal.
No boundary. You mean like the universe has no beginning or end?
Well, it's a bit more nuanced than that. It involves a concept called imaginary time, which is, well, difficult to visualize. But essentially, Hawking's proposal suggests that the universe, when described in imaginary time, is finite, but has no boundaries. It's kind of like the surface of a sphere. It's finite, but it has no edges.
So you're saying the universe might not have a beginning or an end in the traditional sense? It just is. That's a pretty mind-blowing concept.
It definitely challenges our typical way of thinking about time and the beginning of things. It's one of the most intriguing ideas in cosmology.
It's certainly a lot to take in.
Absolutely. And there's still so much more to explore in a brief history of time, like the strange world of quantum mechanics and the ultimate quest for a theory of everything.
Okay, so we've talked about the expanding universe, the Big Bang, and even the possibility of a universe with no boundaries. But A Brief History of Time also touches on another fascinating topic, quantum mechanics. I have to admit, this is where things start to get really fuzzy for me. What exactly is quantum mechanics?
Quantum mechanics is the theory that describes how things work at the atomic and subatomic level. It's a completely different way of thinking about the universe than classical physics. Think of it like this. In the everyday world, we can predict how things will move and behave with pretty good accuracy. You throw a ball, you know where it's going to land. But in the quantum world, things are much more uncertain.
Yeah, it's like there's a fundamental fuzziness built into the fabric of reality at the smallest scales.
Exactly. One of the key principles of quantum mechanics is Heisenberg's uncertainty principle, which says you can't know both the position and the momentum of a particle with perfect accuracy. The more precisely you know one, the less precisely you know the other. It's like nature is hiding its secrets behind a veil of uncertainty.
So even if we had all the information in the universe, we still wouldn't be able to predict everything with absolute certainty because of this inherent uncertainty at the quantum level.
That's right. The universe is not a giant clockwork machine where everything is predetermined. There's an element of randomness and chance at play, especially at the quantum level. And this has some pretty profound implications for our understanding of the universe.
It makes you wonder if free will could somehow be tied to this quantum fuzziness.
That's a question philosophers and physicists have been debating for years. It gets pretty deep. But you also have to consider the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force.
Right. We've already talked about gravity and how Einstein revolutionized our understanding of it. But what about these other forces?
Well, electromagnetism is the force responsible for electricity, magnetism, and light. It's what holds atoms together and allows us to see the world around us. The weak nuclear force is involved in radioactive decay, and the strong nuclear force is what binds protons and neutrons together in the nucleus of an atom.
So we've got these four fundamental forces that govern everything in the universe. But wouldn't it be amazing if they were all just different aspects of a single unified force?
That's the dream of many physicists, to find a theory of everything that would unify all four forces into one elegant framework. There's been some progress in unifying the electromagnetic and weak forces into the electroweak force. But unifying gravity with the other forces has proven to be much more challenging.
It's like trying to fit together the pieces of a giant cosmic puzzle. Maybe that's what makes physics so exciting. There's always more to discover and more mysteries to solve.
Exactly. And Stephen Hawking, even while exploring these grand ideas, always emphasized the importance of continuing to ask questions and seek understanding. He believed the pursuit of knowledge is a journey, not a destination.
And one of the most mind-boggling questions he tackled is the possibility of time travel. Is it really possible to journey through time, like in science fiction movies?
Well, Einstein's theory of general relativity does open up some intriguing possibilities. We talked about how massive objects warp space-time. Some solutions to Einstein's equation suggest that it might be possible to warp space-time so much that you create shortcuts or even loops in time.
So you're saying it might be theoretically possible to create a wormhole, a tunnel through space-time that could connect different points in time?
That's the idea.
Mm-hmm.
But there are huge caveats. We've never actually observed a wormhole, and even if they do exist, they might be incredibly unstable and difficult to traverse. Plus, there are all those pesky paradoxes to consider.
Like, what if you go back in time and accidentally prevent your own birth? It makes my head spin.
Those are some of the classic time travel paradoxes, and they raise profound questions about causality and the nature of time. One possible solution is what's called the chronology protection conjecture, which suggests that the laws of physics might somehow prevent time travel to the past on a macroscopic scale.
So maybe the universe has built-in safeguards to prevent these mind-bending paradoxes from happening.
That's one possibility. It's also important to remember that even if we could travel back in time, we wouldn't be able to change the past. We'd be more like observers, watching events unfold, but unable to alter the course of history.
It's both fascinating and frustrating at the same time. The idea of time travel is so captivating, but maybe some mysteries are best left unsolved. Hawking also discusses the different arrows of time. What are those exactly?
The arrow of time refers to the direction in which time seems to flow from past to future. We experience this flow in our everyday lives, but there are actually different arrows of time based on different physical processes.
Give me an example.
Okay, one is the thermodynamic arrow of time, based on the second law of thermodynamics, which says that entropy or disorder tends to increase over time. Think about a glass of water that spills on the floor. It's easy for it to go from order, the water in the glass, to disorder, the water spread out on the floor,
Yeah.
but it's very difficult to go the other way around.
Yeah, once that glass is shattered, there's no putting the pieces back together in exactly the same way.
Exactly, that's the thermodynamic arrow of time at work. Then there's the cosmological arrow of time, which points in the direction of the universe's expansion. As the universe expands, it becomes less dense and cooler.
So you're saying these different arrows of time, based on different physical processes, all seem to align in our universe, giving us that familiar sense of time flowing from past to future.
That's right. But it raises the question of why these arrows align and whether they could ever point in different directions under certain circumstances.
It's mind-boggling to think about, but a brief history of time has really opened my eyes to the vastness and complexity of the universe. Stephen Hawking's ability to explain these incredibly complex ideas in a way that's understandable, even for someone like me who's not a physicist, is truly remarkable.
Yeah, he had a gift for taking the most mind-bending concepts in physics and making them accessible to a wider audience. And he never lost sight of the wonder and awe that comes from contemplating the universe and our place within it.
So for you listening out there, if you've ever looked up at the night sky and wondered about the mysteries of the cosmos, I highly recommend diving into A Brief History of Time. It's a journey that will challenge your assumptions, expand your understanding, and leave you with a profound sense of wonder about the universe and all its possibilities.
And remember, the pursuit of knowledge is an ongoing adventure. Keep asking questions, keep exploring, and never stop being curious about the universe and all its secrets.
Thanks for joining us on this deep dive into A Brief History of Time. Until next time, keep looking up and keep wondering.